Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Alif Aiman bin Asri. So I'm representing my group, which is Group 3, for this case study. The case study that we done is tutorial 2.1 question 4 and tutorial 2.2 question 1 using the Thevenin and Norton's theorem. So we'll go through quickly for the tutorial 2.1 using Thevenin. So the question asks for voltage and current for the load resistor, which is RL. The load resistor is 1000 ohm, which is RL is in the middle at the terminal 1 and terminal 2. Terminal 1 is the first terminal is consisting R1 and R2, which is R1 is 330 ohm and R2 is 680 ohm, same goes to the R3, and R4 is 560 ohm. So in order to get the voltage and current for the load resistor, we must find VTH and RTH. We'll go through for the first one, which is VTH. In order to get the VTH, we must find the voltage that is come out from the first terminal minus voltage that comes out from the second terminal. So in order to get the voltage that comes out from the first terminal and second terminal, we must use the voltage divider, which is the V out equals to V in times with the resistor. So as we can see, the first terminal V1, it is consisting R1 and R2. So the V out, which is the V source, voltage source, times with R2 divided by R2 plus R1, which is 24, in bracket 680 divided by 680 plus 330, and we'll get 16.158 volt. 16.158 volt is the voltage that comes out from the first terminal. Same goes to the V2, which is the second terminal. Just use the same voltage divider, as the VS is still the same, 24 volt, in bracket 560 divided by 680 plus 560. The 560 is from the R4. You must put first at the upper divider is the resistor at the end of the terminal. So the R4 is 560 divided by 680 from the R3 and plus the R4 560 ohm, and we'll get the V that comes out, and we'll get the V2, which is the voltage that's come out from the terminal 2, is 10.839 volt. Then we already get the V1 and V2. So just in order to calculate the VTH, just minus V1 minus V2, and we'll get 5.319 volt. This one is 16.158 V1 minus by V2, which is 10.839. So we already got VTH. As you can see, at the second circuit, we already eliminate the resistor at the VTH because we're using the Thevenin theorem. And at the left side of the terminal, at the left side of the VTH is terminal A, and the right side is terminal B. So VTH is considered as eliminated from the circuit. So we gonna draw the current flow from terminal A to terminal B. And now we have to find RTH. In order to find RTH, we must calculate the circuit parallelly based on the circuit from A to B. So this is RA is representing R1 and R2, meanwhile RB is representing R3 and R4. So just use the common calculation to find the RA, which is 1 divided by RA equals to 1 divided by R1 plus 1 divided by R2, and then we will get the RA, which is for the first parallel terminal, and RB for the second one, which is R3 and R4. Just insert the calculation and we will get the RA is 222.178 ohm, and meanwhile RB is 307.097 ohm. We already got RA and RB, so just combine together and we will get the RTH, which is the R total, 529.275 ohm. So RTH. Then we can use the equilibrium circuit to easily see the flow of the circuit, to find the current for the load resistor and voltage for the load resistor. In order to find the current for the load resistor, we must use the formula IRL equals to VTH. We already have VTH, divide by RTH times RL, which is load resistor. So we'll get the answer in ampere as the format. We can see 3.478 times power of 10 negative 3 ampere. To minimize it, just divide by 3 and we'll get the answer in milliampere, 3.478 milliampere for the current load resistor. And for the voltage load resistor, just use the formula VRL equals to IRL times RL, which is the load resistor, 1000 from the question, and we will get 3.478 volt. Alright, now we're gonna see the simulation for the Thevenin for the tutorial 2.1 question 4. So this is the software that we use. We use the Volstat. Volstat is the software to calculate the circuit, and this software don't need to download in the laptop or the personal computer, but we can find it in the browser, just directly from the browser. So what we have to do, if you enter the Volstat, it will have the black background. So how to use it? We just go to the draw and then go to the inputs and sources, and we'll go to the add voltage for 2 terminal, and then we're gonna draw the voltage source and add resistor. So this is the R1, alright, and then this is R2, and this is the load resistor, and this one is R3. Make sure the terminal is connected, and this is R4. So what we have to do now is we must connect the end of the terminal by using add wire. And then from the voltage source, we connect the first terminal and second terminal, and make sure the wire or the line of the drawing is in color. As you can see, the green color means it is from the positive terminal, and meanwhile the red color is from the negative terminal. And then you can set the value, which is the voltage source 24. R1 is 330 ohm. R2 is 680 ohm, and the load resistor is already 1000, so we don't need to add another value. And R3 is 680 ohm, and lastly R4 is 560 ohm. The value is already, and click run. Click run and we'll get the value for the load resistor. So as you can see, the load resistor is already eliminated, so it will be the blue in color for the selected one, and the current for the load resistor is 3.479. If you look back to the calculation that we did, we get 3.478 volt, which is the difference is 0.001. So it has proven that our calculation for the Thevenin is same, goes to the simulation. So it has proven. So moving on, we'll go to the tutorial 2.2 question 1 for the Norton's theorem. Okay, for the Norton's theorem, we have to determine the current that flows at the R5, which is resistor 5. And as you can see, the question give the voltage source 8 volt. The first resistor R1 is 5 ohm, R2 is 20 ohm, R3 is 5 ohm, R4 is 15 ohm, and R5 is 10 ohm. So we have to find the current for the R5 using the theorem of Norton's. So what we have to do now, we have to draw the circuit for the as we can see, the question asks for the current at R5. So what we have to do for the Norton's theorem is to do a terminal A and B at the R5 and exchange it to the IN, which is we do a short circuit for the Norton's theorem, because if we did the Norton's theorem for the particular resistor, to find the voltage or the current, we must do a short circuit. So what we already did is we short circuit at the R5 by putting the terminal A and terminal B and I Norton's for the current Norton's. So why IN is equivalent to the current that flows at R3 and I2, because the R4 is no current is flow at the R4, because we already removed the R5, so there's no resistor, and then the current will flow to the terminal that have a minimum value of resistor. So the R5 that just now is 10 is already eliminated, then there's no resistor, so the current will tend to flow at the R5. So that is proven that there's no R3 here. There's no R3 because the R2 will flow directly to the R5, which is IN, and the R4 is abandoned because it has the maximum it has a higher value of resistor. So in order to find the current at R5, we will use the we will use the current divider, which is Ix equals to Req divided by Rx times IT. Then we must calculate the IT using the formula of voltage source divide by R total, and R total we can get from the divider of R3 divided by R2 plus R1. R total just calculate like usual without including R4, because R4 is already eliminated because the current is didn't flow through the R4. So we'll get the RT, which is 9 ohm, using the formula, this R3 divided by R2 plus R1 formula. And then we already have RT, and we can insert the value of RT to find the current total IT. So 8 divided by 9, we will get the current 0.88 ampere, and the I total that we already calculated, we insert in the current divider, which is needed the IT value, and Req is the resistor equivalent. We divide by the Rx, which is the particular current that we want to find, which is I2. We have to find the I2. That the I2, because the I2 is equals to the IR5, which is the same current that flows through the R5. So if you find the I2, we automatically will get the IN, which is I Norton. So just using this formula, just using the current divider formula, insert the value of IT, R2 and R3, which is already given in the question, and then we will get I2 is equals to 0.711 ampere, which is the IN. So next one, we will this is the circuit for the flow of terminal A and terminal B. As just now I said that the terminal at R5 is already dot as a terminal and B terminal for this Norton's theorem. So we will sketch the flow of the current flow from the terminal A to terminal B, so that you can easily calculate the RA and RB. RA and RB is consisting how, in order to calculate the RN, we must use the calculation of 1 divided by Rn equals to 1 divided by Rb, 1 divided by R4, and then at the end we'll get the Rn is 5.625 ohm, and this one is the equilibrium circuit. It is easy to see that at the end we are using in order to get the IR5 current for the resistor 5, we are using Rn equals Rn divided by Rn plus Rx and times by In. So this is also a current divider. I will erase this one. Okay, so this is the current divider for the final answer, and then just insert the value of Rn, which is 5.625 divided by Rn again, and plus Rx, which is 10. Rx is R5. The value of R5 is 10, so that's why we put it 10. We put here 10, and In we already get here, which is the current of I2, and then we will get the answer. The total answer is 0.256 ampere. Moving on, we will see the Norton simulation. So just like the Thevenin circuit, click draw, inputs and sources, and add voltage source photo terminal. Just same goes to the Thevenin circuit just now for the tutorial 2.1. Add the resistor, so this is R1, R2, R3, R4, and lastly R5, which is the current that we have to find. And then just make the wire align together so that we can connect the end of the terminal to make a complete circuit. Okay, so the terminal is already connected, and now we have to change the value. The voltage source is 8, the R1 is 5 ohm. We change the R2 for 20 ohm, 5 ohm for R3, 15 for R4, and lastly 10 ohm for R5. And the circuit is complete, and click run. I'll zoom it a little bit and click run, so you can see, you can click the current that we want to find, which is the terminal R5, and we'll get the current is 256 milliampere, just as we get in the calculation for the Nortons. Yes, 0.256 ampere. So that's all from me. I hope that my explanation is clear enough, and thank you for visiting and evaluating our group. Thank you.